This is the fourth part dealing with EEG montage. It will be conducted in a question and answer fashion. The first question: average referential montage are adequate for A. Detection of localized fields, B. Detection of wide fields, C. Electrode artifacts, D. All of the above. We could say about average reference montage that they are adequate for about everything, but excellent for nothing. This figure represents an average reference montage. As you can see, all cephalic electrodes combined enter through input 2 of the differential amplifier, including the one that goes in through input 1. In this frame, the electrode going through input 1 is represented in aqua. So, as we previously stated, the average differential montage is adequate for detection of localized and widely spread currents, symmetry, and electrode artifacts. So the answer to this question is D, all of the above. Next question. The average referential montage should contain at least dash cephalic electrodes A10, B16, C24, D8. The answer is 16. So the answer to this question is therefore B. Next question. In average reference montage, the prefrontal electrodes FP1 and FP2 and the anterior temporal electrodes F7 and F8 can be omitted from the average to reduce contamination by eye movements artifacts. A true, B false. In the usual average reference montage, as we previously said, all cephalic electrodes combined enter through input 2, including the one that gets in through input 1. And again, I have represented electrode 1 in this frame in aqua. One variation, as presented in this new frame, is to exclude prefrontal electrodes FP1, FP2, and F7 and F8 from the average to reduce contamination by eye movements. So the answer to this question is A. Next question. In the average reference montage, using the minimum number of electrodes, the value of each electrode contributing to the reference is dash of its own value. A 1/16, B 1/20, C 1/1, D 1/10. And as you can see in this frame, the magic number is 16. That is, if we accept that 16 are the least number of electrodes that can be used to construct an average reference montage. Then this formula becomes appropriate. It implies that the power of the reference electrode corresponds to 1/16 of the value of each electrode used. Hence, a large potential will make a large contribution. So let's say that we have an electron, let's say A electrode with a power of 160 microvolts. Then this electrode will contribute 10 microvolts to the reference. Whereas if we had a smaller potential, that is a potential that is significantly smaller than the previously mentioned large potential, the contribution of that electrode will be small. So let's say that the potential in electrode B is only 16 microvolts. Then this electrode will contribute only 1 microvolt to the reference. So the answer to this question is A. Next question. The average reference montage is good to analyze polarity. A true, B false. In this frame, you can see an average reference montage. This montage is showing a negative wave at FC, at CC, and at PC. The maximal activity is arising from CC. Now in this new frame, you can see that there are positive waves at FP2, F8, T4, and T6. The maximal activity being at F8. In this frame, you can see the isopotential map that results from plotting these potentials. Notice a negative field with its maximum at CC and a positive field with a minimum at F8. The conclusion from interpreting this field is that we are dealing with a transverse dipole. In this frame, you can see the same scalp electrodes now referred to an EKG electrode. The brain EKG derivation shown in this frame demonstrates that the tracing is contaminated by EKG artifact, but in between the EKG complexes, the brain activity can be appreciated. I have highlighted that activity in green in this frame. And as you can see, a prominent negative wave is present in all channels, that is from FC all the way down to T6. The field appears to be maximal at CC. In this frame, you can see the isopotential map corresponding to this activity. Notice that it is consistent with a vertical dipole maximal at CC. Now I have placed both isotope maps side by side so you can better appreciate their differences. This one, which would be interpreted as transverse dipole, is wrong. And this one, that is the one on your right, indicating a horizontal vertical dipole, is correct. The explanation is that the vertex wave entering through input 2 has a much higher amplitude than any other wave entering input 2 at the time. Hence, its contribution to the average reference is disproportional. That is, it's proportionally big when compared with the contribution of the activities from all other channels. The moral of the story is not to use average reference montage to determine polarity or to draw an isopotential map. So the answer to this question is false. Next question. The average reference montage is adequate to detect medium amplitude radar localized fields. A true, B false. Average reference montage, as we have previously said, are adequate for localizing asymmetry detection and frequency interpretation but they are not excellent for any of those. So the answer to this question is A, true. Next question. In a weighted average referential montage, all electrodes contribute equally to input 2, except for the electrode connected to input 1, which is not connected to input 2. A, true, B, false. As you can recall from a few seconds ago, when we were talking about average montage, indicated in this frame by its initial, A for average, R for reference, and M for montage, the number of electrodes connected through input 2 includes all electrodes, and all electrodes contribute the same to the reference. On the other hand, when we use weight average reference montage, the number of electrodes coming through input 2 of each amplifier do not include the electrode coming through input 1. And in addition, the weight of the electrodes entering through input 2 varies according to their proximity to the electrode entering the differential amplifier through input 1. The electrodes entering input 2 that are closer to the electrode entering through input 1 weighs more than those further from it when determining the average potential. So the answer to this question is false. Next question. Weighted average reference montage reduces the possibility of widespread activity contaminating the reference electrodes. A, true, B, false. Weighted average reference montage reduces the possibility of a widespread activity contaminating the reference. So the answer to this question is A. Pierre Simon Laplace was a famous electroencephalographer. A, true, B, false. Pierre Simon Laplace was a mathematician. So the answer to this question is false. Next question. Laplacian montage compares the electrode connected through input 1 to the neighboring electrodes coming through input 2. A, true, B, false. Let us say that we want to look at C3 using a Laplacian montage. Then the electrode of C3 is connected to input 1 of the differential amplifier, and the surrounding electrodes will be connected to input 2. We can summarize this arrangement with the following comments. The electrodes going to input 1 does not go to input 2, and only the electrodes closer to input 1 contribute to the reference. So the answer to this question is true. Next question. In Laplacian montage, input 2 always receive at least 4 electrodes. A, true, B, false. This frame depicts the relation between a differential amplifier and the Laplacian montage. Such a relation diminishes the influence of the surrounding potentials, here represented under the green circumference, which are at least in this case 4. An issue with the Laplacian montage arises with edge electrodes, which as you can see are quite a lot. In order to explain the edge phenomenon in Laplacian montage, let's look at T8. In this case, there are only 3 cerebral electrodes surrounding T8. So, only the potentials from those 3 electrodes will be going into input 2 of the differential amplifier, to be later processed by the Laplacian method, which is a mathematical process. Hence, comparison with other electrodes receiving 4 electrodes through input 2 will be fraud. That is the comparison of electrodes at the edge who only enter through input 2, 3 electrodes, to those in the middle who have 4 electrodes entering through input 2. So the answer to this question is false. Next question. Laplacian montage has a complicated formula. A true, B false. Although the Laplacian theorem is complicated, and so is the formula that we use to find Laplacian mathematically, there is a way to understand the Laplacian montage math in a rather simple manner. Let's start by labeling the electrodes in question by the letter X. I will use the term NAV to indicate neighboring average, that is the average of the power of the electrodes surrounding the electrode in question, and the letter P will stand for power or amplitude. So the Laplacian montage gives X, as you know, the value of X minus the neighboring electrodes. But this is not done in a straightforward addition, nor is it a pre-differential amplifier process. I will first illustrate what would happen in a straightforward fashion when the 4 surrounding electrodes are used to formulate a Laplacian. It is important to stress that the process I will be referring to takes place after the raw data is processed by the differential amplifier. So if, for example, we give X the value of minus 50 or negative 50 and give different values to the surrounding electrodes, as you can see in this frame, and we use a straightforward relation between them, then the X electrode and its neighbor will be or will have a 1-to-1 ratio. This is not what happens in Laplacian montage. In Laplacian montage, we can consider the value of X as being X, that is the power of X minus the average of the power of the surrounding electrodes divided by 4. This is, I hope, slightly clearer represented in this equation and depicted in this figure. This will lead us to a 4-to-1 increase in the power of X in relation to the power of the surrounding electrodes, or a 4-to-1 increase in the power of X. Another way to consider the Laplacian montage, or at least to rationalize the Laplacian montage, is to multiply the wave in question, that is the x wave, by 4, and then subtracting this result from the magnitude of the surrounding electrodes. This operation is further represented mathematically, as you can see, by the pointed arrow, and diaphragmatically just below. In any case, the end result is again a 4-to-1 increase in the power of x, that is, of the ref electrode in question, regarding the surrounding electrodes or the reference. So the answer to this question is true. It is complicated. We can visualize it simply by just following the steps I previously mentioned, but that is not close to the mathematical equation and know-how needed to understand the Laplacian montage. Next question. Laplacian montage is the best montage for demonstrating highly localized wave forms regardless of amplitude. A true, B false. Laplacian montage are good for localization. As a matter of fact, they are excellent for localization, to the point that they are often called source localization montages. In this epoch, you see two rectangles enlarging two waves. The wave within the dark orange rectangle has a phase reversal and a narrow field. The other wave in the blue rectangle does not have a phase reversal, and it has a more widely distributed field. Now in the Laplacian montage, the T4 is very prominent, and the wave with no phase reversal, the one in the blue rectangle, is less noticeable. So the answer to this question is true. Next question. Localization in Laplacian montage is based on amplitude. A true, B false. Localization using Laplacian montage is based on amplitude. The apostrophe in the second T4 implies neighboring electrodes. So the answer to this question is true. Next question. Laplacian montage has a significant spatial filtering effect. A true, B false. The filtering function of an EEG can be referred as frequency driven. In this case, the amplitude of a wave is reduced a large or a small percentage according to its frequency. This type of filtering is accomplished by the introduction of filters, mechanical or mathematical, into the EEG machine, and also by the effect of tissue, that is CSF, meninges, skull, and scalp, between the generator and the EEG recording electrode. A different type of filters, a function of distance and position of the electrodes in relation to each other, is spatial filtering. In spatial filters, the amplitude of a wave is reduced more or less according to the area that generates the potential. This frame shows the spatial filtering effects of Laplacian montage. In the x-axis, I have depicted the size of the fields, and on the y-axis, the amplitude. The yellow bar on your right depicts the effect of Laplacian on the amplitude of a potential generated by a narrow field. The yellow bar on your left depicts the effect of the Laplacian montage on the amplitude of a widely spread field. And the yellow bars between these two figures represent the gradual effect on amplitude that the Laplacian has. The gray bars represent the amplitude of the same potential would they had been captured using a relative distant neutral reference. As is shown here, Laplacian montage has an excellent spatial high-pass filter effect, allowing detection of very localized neutral current sources. Laplacian montage allows detection of very localized fields by decreasing the amplitude of the wave involving the wide area around it. If I had my way, I would not use the term spatial high-pass filtering effect to describe the filtering effect of Laplacian montage. I would use a spatial narrow-pass filtering effect, since what it lets through are potentials generated by narrow fields. So I would say that the Laplacian has a good narrow-pass filtering effect and a wide spatial filtering effect, implying that wide fields are reduced significantly in amplitude. So the answer to this question is true. Thank you very much for your attention.